Hey everyone, we're jumping into analytical chemistry today. But listen, forget the textbook for a sec. I want you to picture this a little differently. Think of it like a mystery, and you're the detective. Ready to start the investigation? All right, so picture this. You're in the lab. In front of you, there's a test tube. Inside, a totally mysterious salt solution. I mean, it could be anything. Your mission is to figure out what it is, to unmask its identity. This, right here, is what analytical chemistry is all about. So, where do we even begin? All right, every good detective needs a clear mission, right? So, in this first part, let's nail down our objective, finding out what that mystery chemical is that's hiding right in front of us. So, this whole detective thing we're doing, it actually has a proper name in chemistry. It's called qualitative analysis. And really, all that means is we don't care about how much of the substance there is, we just want to know what it is. And for our mission, we're hunting for a very specific culprit, the cation. That's the positive metal ion lurking inside our mystery salt. Okay, so any investigation has to start with just looking, right? Observation. And lucky for us, a lot of these chemical suspects aren't that great at hiding. The very first clue is usually staring us right in the face, the color of the solution. And check this out. This is so cool because right away, we can start narrowing down the list of suspects. If your solution is blue, bam, you're probably looking at a copper ion. Got a light green color? That's a huge pointer to ferrous iron. But what if it's clear, totally colorless? Now that's when the real mystery starts, because that could be calcium, zinc, or lead. So, to figure out which of those colorless ones we have and also to double check our hunches on the colored ones, just looking isn't going to cut it. We need to get a little more active. We need to interrogate our suspects. And for that, we need our detective toolkit. And in that toolkit, we've got two main tools, our interrogation specialists. First up is sodium hydroxide, or NaOH. I want you to think of this one as the strong interrogator. It's a strong alkali, and it'll get a reaction out of pretty much anyone. Then we have ammonium hydroxide, NH4OH. This one's our subtle interrogator. It's a weak alkali, and it's perfect for those really tricky cases where two suspects look almost identical. Okay, so we've got our tools. Now what? We gotta learn how to use them, right? When we bring these guys in, what kind of confession are we even looking for? Let's break it down. So check this out. When we add our alkalis, something really cool happens. Our cations, our suspects, they react and form these solid metal hydroxides. Now, these solids are insoluble, which just means they won't dissolve. They kind of just appear in the test tube. We call that a precipitate. And here's the best part, the real giveaway. Each one has its own unique, distinctive color. That, my friends, is the confession we're looking for. But hold on. A good detective never just takes the first confession at face value, right? You gotta be sure. So it's a two-step process. Super important. First, you add just a few drops of your reagent and you make a note of the color. Then you go a step further. You add more of it, what we call an excess, to see if that solid thing, that precipitate, disappears again. This second step, that's our lie detector test. It's how we know for sure who we're dealing with. Okay, and this right here, this is the Holy Grail, our evidence board. This is your cheat sheet for the whole investigation. Let's run through it real quick. Take a look at copper. It gives you a pale blue precipitate with both of our interrogators. But see what happens when you add extra ammonium hydroxide? Whoosh! It dissolves and turns into this incredible deep blue solution. Awesome. Now, what about iron 2 and iron 3? Super easy. They give you those really obvious dirty green and reddish ground colors. And they don't dissolve in anything. Dead simple. But now for the tricky part. Look at zinc and lead. They both give away precipitate. So how in the world do you tell them apart? Well, the secret is in that ammonium hydroxide column. The zinc precipitate, it dissolves in the extra stuff, but the lead one, it stays put. And that is the clue that cracks the case. All right, we've gone over the evidence. Now it's time for the fun part, putting it all into practice. So let's put on our detective hats and solve a couple of classic cases, the kind you are absolutely going to see. So here's the scene. You've got two test tubes. Both have clear, colorless solutions inside. You add a little bit of your strong interrogator, sodium hydroxide, to both of them, and you get a white precipitate in each one. You know one of them is zinc and the other is lead. So, what's the move? How do you figure out which is which?
The key here is to bring in our subtle interrogator, ammonium hydroxide. So you grab fresh samples and you start adding it drop by drop. And at first, you're going to see that white precipitate form in both test tubes, no big surprise. But the next step, the final step, that's where the magic happens. You add excess.
And here it is, the big reveal. In the test tube with the zinc salt, that white stuff, it completely dissolves. Gone. You're left with a clear solution. But in the test tube with the lead salt, that white precipitate just sits there. It is stubbornly insoluble. And just like that, case closed. That one test is the surefire way to tell them apart. Okay, let's do another one, a quicker case. Iron 2 versus iron 3. How do you tell these two apart? Honestly, this one's a piece of cake. It doesn't even matter which reagent you use, sodium hydroxide or ammonium hydroxide. The results are totally obvious. Iron 2 gives you that unmistakable dirty green color. Iron 3, it gives you that classic reddish-brown, rusty-looking precipitate. The colors say it all. Easy. Now, hang on a second. You might have noticed something a little weird back on our evidence board. Remember how some of those precipitates, like the ones from zinc and lead, actually dissolved when we used the strong alkali NaOH? Why would that happen? Well, it's because they're part of a special group of suspects. This special group is called amphoteric hydroxides. The best way to think about them is like chemical double agents. They kind of play for both sides. They have this dual personality that lets them react with acids, which is normal for a base, but they can also react with strong alkalis. It's pretty unique. The main double agents you really need to remember are zinc, lead, and aluminum. And it's not just them. Their oxides and hydroxides do it too. They all have this special amphoteric power. They play for both teams, chemically speaking. And that right there brings us full circle. That's why the white precipitates from zinc and lead dissolve when you dump an extra sodium hydroxide. It's their double agent nature kicking in. They're actually reacting with that strong alkali to form something new that's totally soluble. It's not magic. It's just chemistry, their special amphoteric nature at work. So, why did we go through all this trouble playing chemical detective? Well, it's because getting a handle on these techniques, knowing your colors, knowing what dissolves and what doesn't, is so important. In fact, this whole topic usually adds up to about 5 marks on your board exams. That's 5 marks you can totally lock down just by being a good detective. And with that, we're at the end of our investigation. But I want to leave you with one last thing to think about. We've talked about these amphoteric hydroxides and how they can act like an acid and a base. So what does that really tell us? What does that double agent behavior say about the deep, fundamental nature of elements like zinc and lead? It's something to chew on, right? The case might be closed for today, but the bigger mysteries of chemistry, they're always out there, waiting to be solved. Thanks for joining me.